what we're going to do this afternoon is ideal voltage sources. We're going to look at using a theorem called Thevenin's theorem to analyse DC circuit. So this will really be, unless you've done electrical principles to this level before, you probably wouldn't have done Thevenins theorem. You might have done it, uni. Yeah. Okay. So first of all, before we can use the theorem, we need really to understand what's meant by an ideal voltage source, and then also how we can represent a real world, or simulate, or represent a real world voltage source. If we had an ideal voltage source, Vs for 10 volts, what that would suggest is that it would always deliver 10 volts to the load that it's supplying, in this case RL, regardless of the value of RL, and hence regardless of how much current we drew from that circuit. So here I've got current on the x-axis, and if that source is ideal, it would remain a 10 volt output voltage there, regardless of how much current. So regardless of whether I drew 2 amps, 10 amps or 100 amps, that would still give me 10 volts. That's what we mean by an ideal voltage source. Okay. Now, in the real world, they don't exist. You cannot get a voltage source that's ideal, will always deliver the same voltage regardless of current. It's not possible. So it means, that would mean that VL is equal to VS for any value of load. Okay? Any real voltage source can't achieve that situation. Alright? So what we need is a way to represent a real voltage source. Just going back to that diagram, here we have, if those two terminals indicate everything inside that, indicate the ideal voltage source. Then there's no resistance in that part of the circuit. An ideal voltage source has no internal resistance. Yeah. Now, when you think, if you think of a generator being a voltage source, it must have internal resistance because its windings are made up of copper wire that, although quite low resistance, they have some resistance. So this ideal voltage source is fictitious or scientific in a way, and it's a voltage source that doesn't have any internal resistance. That's an important point to remember that. Sorry? Pi? It's not imaginary, but it's abstract in the sense of, in real life, we can't make one. Okay? Yeah, we cannot have a battery or the generator at Sizewell Power Station. All of them have some internal resistance. Alright, so what we do is we represent a real voltage source by putting what we call an ideal voltage source like the one on the previous page that has no internal resistance. We put it in series with its internal resistance. Okay, what we're saying is we can represent a real voltage source by having an ideal voltage source Vs in series with its internal resistance called Rs. Yeah. What happens then when the terminals of the circuit are open? If you put a voltmeter across them, because there's no current flowing, you'll measure the full voltage. Okay, but what happens when current is drawn, some of that voltage from the ideal voltage source will be dropped across the internal resistance. So as we draw more current from this power supply, source of power, then your terminal voltage is going to reduce. Right, and if you think about what would happen if you put the headlights on your car and then you turn the engine over to start it, what happens to the headlights? They dim because the starter motor is drawing so much current from the battery it can no longer give the full 12 volts to the headlamps. Yeah. Okay. So if we look at that in calculation sense and have a look at this example, if the open circuit voltage of a battery is 12 volts, so what we're saying there is, what is it? We're saying is if that's 12 volts and it has an internal resistance of 0.5 ohms, find the terminal voltage of the battery when currents of 2 amps, 10 amps and 20 amps are drawn from it. So what we're saying is if we connect in here a load such that first of all 2 amps flows, what we're interested in is what's this terminal voltage, we'll call it V out for the output of that voltage source. So how can we calculate what V out's going to be? .5 times 2 gives me what voltage? If current's going that way, I've got, come on, I'm going to be a nuisance to you all. Say, current's 2 amps going that way. Yeah? So have I not got a volt drop VRS there? Can I not calculate that? Yeah, because I know the current going through it and I know the value of the resistance. So at 2 amps, VRS is equal to, how do I calculate that? Not 0.5 times 2, 1 volt. Yeah. Yeah. And what's giving me that answer? What law is it that will give me what the terminal voltage is now? Formally. We now know, we know this voltage, we know that one, we want to know that one. What have we got? We've got a Kirchhoff's voltage law loop, yeah, that says these 2 voltages should add up to that one. Alright, if we follow the rules we went through, just so everybody understands, we put all the clockwise arrows on one side of the equation, so we can say by Kirchhoff's voltage law, clockwise arrows are Vs, anti-clockwise arrows are VRS plus V out, and then we can rearrange that for V out, can't we? Therefore, V out equals Vs minus VRS. That is 12 minus 1 equals 11 volts. So we draw 2 amps from that power supply. we drop 1 volt across the internal resistance of it, and therefore we only get 11 volts at the output terminal. Okay, so finish that off now for currents of 10 amps and 20 amps. Okay, so at 10 amps, what we got? Yeah. VRS equals 0.5 times 10, 5 volts. Yep. So we're dropping more voltage across the internal resistance. So V out is 12 minus 5, 7 volts. Yep. And then at 20 amps, VRS 0.5 times 20, 10 amps, 10 volts, V8 12 minus 2 volts. So as you can see, as we draw more current, we're going to drop voltage at the terminals, and you get to a point where there's nothing left. Yeah. So when 0.5 times the current is equal to 12 volts, then you're going to get your own situation where you're saturated. We're making the assumption here that power supplies are linear in their output, which may not be the case for all induction power supply. But it's good enough to do circuit analysis that we can do. The important thing to remember from this is that an ideal voltage source has an internal resistance of 0 ohms. Yeah. Okay. And then we represent the real one by saying we imagine it's got a series resistance equal to its internal resistance. All right. So, everybody happy with that representation? So what we're going to do now is start to look at a network theorem. There are a number of network theorems that we can use in electrical engineering, analyse circuits, and make a simplification to make them easier to analyse, that include Thevenin's theorem, the one we're going to look at today, Norton's theorem, which is similar but a bit different, ideal current sources, the superposition theorem, nodal and mesh analysis, maximum power transfer. Okay, we're going to stick to Thevenin's theorem today. We may touch on maximum power transfer theorem in the coming couple of weeks, but we'll be doing maybe 2 or 3 others of that list. We'll do electrical principles in semester 6. Alright? Because this one we're going to do today, there's a particular interest if you want to know how a network is going to act for a number of different values of load resistance. Because you can simplify the circuit, do the difficult calculations once, and end up with a simplified circuit, and then you can put any load resistor in and calculate what current will be delivered to that load with a much simpler circuit. Alright? So that's one of the great values of Thevenin's theorem. Okay. So, Thevenin's theorem, in words, it says, it's not very easy to understand in words, really, but any active network having two terminals, A and B, can be replaced by a constant voltage source of voltage V little t. Notice little t representing the Thevenin voltage. It will have no resemblance whatsoever to the actual voltage source in the original circuit, as you'll see soon. Okay, the value of Vt is equal to the open circuit potential difference between the terminals A and B. And the internal resistance in series, R Thevenins, is equal to the value of the resistance of network measured between A and B, with the load disconnected and all sources of voltage or current placed by that ideal internal resistance. So that's the theory in words. It's far more understandable if we work through an example to a particular procedure. Right? But in summary, what that would do is take a circuit like this. So we've got a voltage source here, 24 volts. We've got 1, 2, 3, 4 resistors. And if this R4 here is the load resistor of interest, and we're not particularly interested in what current is flowing in the other three, yeah, we can use Thevenin's theorem to turn all of that circuit into this simple series equivalent circuit of voltage V Thevenins and internal resistance R Thevenins. So it's become like that model of the real voltage source that we looked at earlier. Because if we take that resistor in isolation, it's these 4 components that is applying voltage to that. So the voltage this resistor sees just was dropped across it. Yeah. So there's simplification. So if you want to know how that circuit would work, if you had 10 ohms, 20 ohms, 30 ohms and 50 ohms resistors connected to it, you can do the complex calculations once, turn that circuit into this one, and then that's quite easy to do a voltage divider and find the current or the voltage to the load using the equivalent circuit a number of times over. Right. And an example will better show how that works. So, there is a procedure to adopt, and if you follow it carefully each time you do one of these problems, you shouldn't go wrong. You take your original circuit and you remove the required load resistor, for which you need to analyse the current from the network, leaving 2 open terminals, A and B. What you then do is use any other techniques that you know, Ohm's law, Kirchhoff's current and voltage laws, find out what the voltage at those 2 open terminals is. Yeah, that voltage will be your Thevenin voltage V little t. Then, the second part is remove each source of voltage or current, and on this module we'll only be looking at circuits that have got one source of voltage or current in it. We won't be looking at dual source circuits. We will in electrical principle. But each source is taken out of the circuit and replaced with its ideal internal resistance. So if we take a voltage source out, what do we replace it with? Yeah, what's the resistance of an ideal voltage source? 0. So we take the voltage source out, we replace it with a short circuit. And then we measure or we calculate the resistance of that circuit looking back in from the terminals A and B. As though we were connecting an ohm meter to the output terminals A and B, what resistance would we measure? That is equal to the Thevenin resistance R little t. Then you can use that equivalent circuit to calculate the currents and output voltages for any value resistor you want to connect to that circuit. So, we're going to use Thevenin's theorem to calculate the current flowing and the power dissipated in a 30 ohm resistor. What you'll find I've done in your notes is repeated the allowed space for you to repeat the diagrams. I think I've included the diagrams of each stage, I'm not sure. Alright, and then towards the end there's some examples for you to have a go at. Alright, so we're going to use, this is going to be our resistor of interest. So that's the one we're going to analyse for and find out what the current through and the power dissipated by the 30 ohm resistor is. Yeah. So the first thing to do in this is to remove that 30 ohm resistor and leave two open terminals A and B. So that's what I've done. So I've got V open circuit, and that V open circuit is equal to the Thevenins voltage for our equivalent set. So what do we got to do to calculate the voltage that would be dropped across here? First of all, ask you a question. How many volts have been dropped under these conditions across R3? An even earlier question than that, which way is current flowing in this wire? Yeah. Yeah. What about here? How much current flow in this one? That current, under current conditions, is 0 amps. Yep. So, how much voltage being dropped across the BR3? Yeah. So if this is, there's a current, if this is VR2, what does Kirchhoff's voltage law say about VR2 and Thevenins? Yeah, because that one's 0, we can say in full by Kirchhoff's voltage law, yeah, we've got a clockwise arrow, VR2, and that's equal to VR3 plus V Thevenin, the open circuit voltage. Yeah, and we're interested in V Thevenin, so V Thevenin is equal to VR2 plus VR3, which is totally correct, yeah. But that's because that's nothing, because that equals nothing, those two are equal each other. Yep. Because that one up there is nothing, by Kirchhoff's law, those two should be the same value. Plus nothing, minus nothing doesn't make any difference to it. What? What do you mean what? Why did we... Go on. Well, you can, but I'm trying to show using the full law, but it stands true. Let me do that again because I made that. So we're interested in V Thevenins, and that is equal to VR2 minus VR3, which is nothing. Yeah, so it's equal to VR2 minus nothing. So if we can find VR2, we've effectively found V Thevenins, is what I'm trying to show you. Yep, because there's no volt drop across that resistor because there's no current flowing through it. No, I ain't got it. There's no value to VR2 yet. We ain't calculated, have we? But looking at that circuit, I mean, not all circuits are the same, of course. But in this case, we've got this series resistor here, but because of the open circuit at the output terminals, there's no current flowing through it. So the open circuit voltage of this is the same as the voltage across R2. So how can we find the voltage across R2? Yep. I equals Vs over we've got two resistors. If we look at that circuit there, we've got R1 plus R2 because they're in series. Yep. So that's 24 over 5 plus 20. I got 0.96. Yep. And then from that we can say therefore VR2 is equal to V little t Thevenins. We've already shown that by Kirchhoff's law there. Is equal to I times R2 0.96 times the value of that resistor 20 equals 96 times 20 19.2. So the first value for our equivalent circuit, V little t, is 19.2 volts. So I can go forward a couple of pages where I've got the diagram of my equivalent circuit on it. Let's say that is equal to 19.2 volts. V7. Yeah. You can see it doesn't resemble the original voltage source that we removed. It's different. Yeah. Now going back one page, what we then have to do is take out the voltage source, which was here, and replace it with its ideal internal resistance, which is a short circuit. I tend to draw them on like that, so you can see that you've actually taken something out and replaced it with a short circuit. Yeah. And always in assignment questions, I would expect you to show these different diagrams. Don't try and do it all on one diagram. Draw a new diagram, take the voltage source out, and put the short circuit in. Right? And then what we're looking at is that R little t is the resistance looking back in that way. So what would be an expression in one go for R little t? What kind of circuit have we got there? think about where current would flow and what options current would have in this circuit. If I put a battery across those two terminals, for instance. So for a minute, if I done that, where would current flow? Through R3, yeah. When it comes here, what does it do? Split. So some will go down there, some will go down there, but that meets up again to be the same. So what type of circuit have I got? How are these two resistors connected? Yeah, so we got one resistor in series in parallel to two other resistors. One resistor in series with two others in parallel. So we can say RT, here R little t is equal to R3 plus, because it's in series with, and then because we only got two, we can do product over sum with those, with R1 and R2. So R1 times R2 over R1 plus R2. If you're more comfortable, right, with not writing that in one go and doing that bit first separately and then adding it to the value of R3, I don't care. Alright? But if you do it in one go, you're only going to round once. That's the only difference. Alright? So we put our numbers in. R3 is 5. R1 is 5 times 20 over 25. So that's 9 ohms, isn't it? Yeah. So our Thevenin's resistance, looking back in from the output terminals, think about how current will flow. It's got to go through, all got to go through that resistor. So that bit and this part of the circuit are in series. So we've got one resistor in series with two others in parallel. Yeah. So going on to our next page where we've got our equivalent circuit, we can say that RT here is equal to 9 ohms. We then, here's our terminals A and B from the original circuit, and put our load resistor back in, and we can calculate the current IR4 high. We're interested in that current, IR. So I've got IR4. Well, that's Ohm's law, isn't it? So it's going to be V, so it must be V Thevenins over is that the only resistor in that circuit? You've got that and that in series. So that voltage is pushing current through both those resistors in series. So you have to add them together. Yep. So that's 19.2 divided by 9 plus . Up until that point, we haven't really gained that much. But the power of this technique comes is if you're interested in what would happen if I changed the load to 20 ohms or 50 ohms, because you can just plug that value in there, put the values, the new resistance value in for R4 in this formula, and calculate that current straight off without doing all those other calculations again. If you use normal techniques, you'd have to do the more complex calculations over and over and over. Right. And then it asks for the power dissipated, isn't it? So PR4 I squared R4 0.492 squared times 30. What's the answer to that? That's the power dissipated by the R4 resistor. It's equal to the current through it squared times R4. But again, somewhere about 7.5. Right. Okay, so are you all happy, reasonably happy with that? Yeah, so if you follow that procedure, take the load resistor out of interest, calculate the open terminal voltage, take the source out and replace it with its ideal internal resistance. So for a voltage source, that's a short circuit. Alright. You end up then with the equivalent circuit that is just one voltage source, Thevenins, in series with two resistors, Thevenins and the load, and you can use that to calculate the current. So on the next page, there's an example for you to have a go at. Determine the Thevenin's equivalent circuit for this network, terminals A and B, and use the equivalent circuit to determine the current and power for load resistors RL of 20, 40 and 60 ohms.